very last lecture of the course in Advanced Quantum Algorithms. So today we will cover some quantum versions of neural networks. Just before we begin, just an addition to the last lecture. So at the very end we discussed briefly the quantum principal component analysis. So I don't think I was clear there about what matrix it is that you are actually finding eigenvectors and eigenvalues for. So we have this, you have a matrix, or you have a number of data points and you want to find sort of the axis along which they vary the most. So the matrix that you are diagonalizing is the covariance matrix of this data. So in the quantum principal component analysis, we find, using the quantum algorithms that we discussed, eigenvalues and eigenvectors for the covariance matrix, which is sum over j xj xj transpose. And so each xj is one data point. Yeah, that's it. I also think I didn't mention last time that this quantum principal component analysis is one of those machine learning algorithms that recently have found where there have been some classical version proposed based or inspired by the quantum algorithms. There is a quantum inspired that's by who was the one who also proposed these first quantum-inspired algorithms. So there were some problems where a quantum algorithm was known and it was thought to be better than the best classical algorithm. But then, sort of being inspired by how the quantum algorithm works, she managed to come up with a classical algorithm that scaled in basically the same way with the size of the problem. Now there are other factors that enter some of these quantum-inspired algorithms, like condition number for matrices and so on, where the scaling is not so good. So these quantum-inspired algorithms might still not work, but it's a very interesting development. Was there a question? Okay, so today, quantum neural networks. This, I would say, well, like much of the quantum machine learning in general, this is very much a field where research is being done now. It's under development. Many things are still unknown. So it's a bit hard to summarize. But I thought I'll try to give you some ideas of what the important things are. So I thought we would start with just, first of all, you thinking for a while, what could be possible advantages or problems if you try to make a quantum version of neural networks. So we briefly discussed how neural networks can work back on Tuesday. So sort of with that in mind, can you think of any possible advantage to have quantum components there? Can you think of any problems that can rise if you have quantum components there? Just take 3 minutes. You can discuss with the person next to you, and then we'll collect input.
Oh, right. I was thinking because I know a problem. I don't know if you mentioned a problem with neural networks is that there are so many dimensions to this all the weights and biases. So it's impossible to find it like the global level, but you can only represent maybe come back into a neural network and find some algorithm that like tries all combinations, every bias and every weight at simultaneously and finds the moment. Maybe.
Is there a problem with getting these step functions? Because that is like steps and you need some non-linear functions, yes. But you get problems with the intelligence functions. It's actually a step thing left to zero or left to one. Maybe you don't need this step, you can what if it's smooth?
Once we have optimized it, that might be super large. A problem I just realized is usually you have a lot of input, like let's say you have a 20 grid, which is your view, and then you have like 10 points, that's just numbers or whatever. That is reversible. So maybe that will be a problem that usually we don't have. Or at least in classical it's reversible, so that it cannot directly be maybe there's some tricks to get around.
Always phrase it in matrix representation, finite dimensions in space. But you there can be some non-linear function with non-linear what? An input in some parameter, I suppose. But I don't know enough.
If what other programs could fit. Yeah, usually neural networks they have thousands of connections and stuff. Then it's hard to, with the current state of qubits, it's
would work
completely big to have that many connections without the connection.
So you, I don't know, maybe your answer is something different than classical neural networks.
Say again.
The sigmoid function or something.
Yeah.
So there's a setting point.
Mm.
Because Because you put like two high themes together and then people will say, take my first one, try it. Yeah.
You're gonna code all data. There should be some speed up to that somehow. So then it's not really a problem.
So the problem is
Right.
Yeah.
Well, I would say still possibly the learning process.
I think
What's not
summer school is
learning
algorithm.
QL
About
that maybe you can
quantum
optimize
neural
your
networks.
network much faster. Because that's basically what the classical
Probably
machine learning is about.
the first thing that
teach you
on computer stuff is used for.
like you send thousands of pictures of
No.
different things and then you
Solving
have to learn how to
optimization
recognize
problems or
this and that.
something. This is what
Possibly
really
there could be some
neural networks. The argument. I just remember one of the arguments was that you can represent that. Just but they had many more arguments that I don't remember correctly.
Okay, seems to be interesting discussions here. So, Pontus, Oliver, would you like to start? Give us one advantage or one problem?
Yeah, an advantage is that you can represent an input vector of length n with log 2n qubits.
Okay, so compact representation input. So this is some kind of quantum random access memory then we need? I think.
Yes, and I guess that's a problem then. That you need to input your data.
Possible problem, possible advantage. Okay. Next group we have.
we mentioned an advantage could possibly be that, like you know how the classical machine learning is basically about optimizing thousands of different parameters and weights and biases. Possibly there could be some quantum algorithm where you can kind of try all combinations of the weights and biases at the same time and find the optimal
So some kind of
learning optimization, quantum learning optimization algorithm, QLOA, you know.
quantum speed up for learning.
Possibly.
Okay.
The advantage we have is the same thing. Maybe
This learning.
yeah.
Yeah. Okay.
And disadvantage probably you need a lot of qubits. But
Okay. So why would we need many qubits?
for each layer,
Yeah, because in each layer there are many nodes in the network, so it's hard to
unless you find a way to reuse.
Okay. More? Any advantage or problem with that one?
I don't know much about neural networks, but maybe one gets a problem with nonlinear functions because quantum mechanics is a linear field.
So lack of nonlinearity. Yeah, so on Tuesday we discussed each neuron has this activation function, this is some nonlinear function. And this is important to be able to represent functions working with the whole network. And yes, that's not clear how to get it from quantum. Anything else?
It's hard to speed up the learning process, right? So
Okay.
we need to do the environment to train.
Okay, yeah. Okay, so how do we say this? Yes.
And usually we use QAA, something similar algorithm to.
So it could be that many measurements are needed.
Does measuring introduce nonlinearity?
That could be a way to introduce nonlinearity. We will actually see something like that later.
There are many connections needed. Like usually every layer is connected to all the neurons of the previous layer, but that's really a problem today, at least when we fabricate stuff, to connect them to each other without losing the coherence.
Yes. So, yeah. Well, okay. You see there are many problems, but unclear advantages. Okay, anything else you thought of? Yeah, I would say this is very good. More than I had written down on my list. So I would say, you remember, I think it's probably covered by some of these, but you remember an important step or important trick to be able to train fast, to update the parameters fast, was that you could compute the gradient in a clever way with this back propagation. And that is sort of unclear how to do, because you need to measure sort of what the parameters and states are at each point in the network, and you propagate back using this information. But if you do a measurement in some quantum network, then you're affecting things in a way that you don't. So it's sort of unclear how to do back propagation. And then for advantages, well, you talk here about this, maybe you can represent the input in a way, in a compact way. One thing could be that maybe you can deal with actual quantum input, like some quantum data from some quantum systems in a way that classical networks find. Okay. Let's see some examples, recent proposals for how a quantum version of a neural network could look. If you remember, one person who can said to be the inventor of the QAA algorithm that you studied earlier was Ed Farley. So he also has a paper from last year, or a preprint, together with Hartmut Neven at Google. And there they describe sort of a possible quantum version of a neural network. So what do they have in mind? Well, they think about a circuit, a quantum circuit, where, let's see, you have n qubits that represent some input state. We can call it Z, following their notation. And then you have ancilla qubit, so an auxiliary qubit helper. This is, yeah, we discussed this last time, like what does ancilla mean? So I checked now, there is some ancient Latin word for like a servant or maid, but yeah, that's what ancilla originally means. And some of that connotation is on there, this help, yeah, it's a helper qubit. So then this input and this ancilla, they are now going to be subject to some gates. So for example, these two qubits are acted upon with some unitary operation, which is parameterized by some angles, parameters θ1. Maybe and then maybe you take the output with the first qubit and then some other qubit, and they are acted upon with some other operation. So you have a bunch of 2-qubit gates and you apply them between different pairs of qubits, including this ancilla qubit. And then you have some output, and you measure in the end this ancilla qubit. And they call this, they do a measurement on Y. I think it's really not important. You measure some variable there that is plus or minus 1. So this whole circuit is some huge unitary parameterized by parameters θ. So the idea here is that this is a classifier. And it classifies this input state Z as belonging to one of two classes. The result is given by measuring the ancilla. And you get plus or minus 1. That's your two classes. And maybe you need to run this circuit several times to get statistics. Maybe like on average you get plus 0.8. So, would you say this is a quantum neural network?
It's
It's a one neuron, but it's
You think it's one neuron?
yeah, because it can only do biclassification.
Yeah, okay, so you mean I guess you could imagine having a second ancilla qubit there and then doing classification into more classes by measuring 2 ancilla qubits, and you could get 4 different results, for example.
in classical neural networks, this is the question.
Yeah.
Can you represent, so input, output is equal to input into some matrix, a huge matrix?
No, because you have these nonlinear
No,
activation
no.
functions along the way.
Okay. But if it is linear, if the
If it's linear, then I guess you can do that.
and okay.
Probably.
Is that what they're doing here?
Yeah, you could say this unitary operation. You can write it as a huge matrix acting on the input state. And so you notice that it's instead of sort of having these neurons in the classical networks, we instead now have gates that act on pairs of qubits or single qubits. So in a way, we don't have this property, like in a classical network, especially if you have fully connected layers, then you have inputs from many different neurons being fed into one. Although I guess you could sort of arrange that with a number of 2 qubit gates in sequence here too. And you have sort of similar to the classical neural networks, you have a lot of parameters. There in the classical network you would have these weights and biases. Here you have all these parameters theta for different gates. And so you can imagine training this for sort of finding a good set of parameters to do this classification task. But there's, for example, this nonlinearity is nowhere to be found here, as far as I can understand. So, yeah.
In that paper, does it work?
So they do some small simulation because, I mean, it's hard to simulate large quantum systems. So they can, I think they do the MNIST data set, these like handwritten characters, a small version of it where it's just 4 by 4 pixels. So they can simulate this with 16 qubits for the input and 1 And it's not on some actual machine, but just numerical simulations. And I don't think they could show any advantage. It's inconclusive. Yes. So how do they train this? Well, they have a loss function. So as a function of the parameters and input, they define it as 1 minus L of Z. And this is, so Z is the input. This L is the correct label. So it's plus or minus 1. So we have some training data set. And then you're multiplying that with expectation value of the final state so U acting on Z and 1, that's the whole evolution of this network, and then you get this final state, and you're doing the expectation value of this operator Y n plus 1. So this is the measurement that's supposed to give you the label, plus minus 1. It can be some value in between, because it's the expectation value. So if it's the correct label and the expectation value the same, then this cost loss function becomes 1 minus 1. So it's if the correct label and the expectation value disagree, then you get something larger than 0. So we want to minimize this loss function. Okay, so how do they do this? Well, what they propose to do is to train with gradient descent. Or to be more specific, is stochastic gradient descent. Does anyone remember what stochastic gradient descent is? Can you tell me?
You didn't use the whole data set.
Exactly. Yeah, so to calculate the loss function, I don't use every single example set in the input, I just use a subset of them to take one step to find the gradient and take one step, and then next time I use another subset of the input. So I don't have to run this as many times as I otherwise would. They show that one possible advantage here, if all these U's are unitaries, all these U's are unitaries, on the form sine theta sigma, where sigma is product of Pauli operators. And they show that because they have this form, they can say something about the gradient for this function. They can say that the gradient is bounded. And they say that at least this avoids one possible problem in classical machine learning where the gradients can sort of flow up in some situations. Let me get some space here. Now you could ask, so is this, you remember we discussed for the classical neural network there was this old theorem by Sevenko showing that with a single hidden layer you could represent any function, any smooth function. So you can ask, well, will we be able to represent any function here? And they proved that for this type of network, they can represent any label function. Any label function, L of Z. But it may require exponentially deep circuits. Now, they say they do this stochastic gradient descent. So that saves some time by just using some of the input in each step. But how do they actually compute the gradient? And basically they give two methods for it, but it pretty much boils down to the more naive gradient computation you need to do. So you need to do vary one parameter at a time, get one partial derivative at a time to get the whole gradient. So they cannot do back propagation. So this, in my understanding, this is the biggest problem. It's that you can't do back propagation. So they need to run this circuit many times to compute the gradient instead. So the training should be slow. I don't think they really notice it for the small instances that they simulate. It's just 16 qubits. But I think it would be a problem if they try to scale this up. So this is sort of an example of how you could imagine a quantum version of a neural network, but it seems slower to train. I think back propagation is the big thing that really gains you orders of magnitude in training time in classical networks. And sure, they can it has representation power, but that might require very long circuit, very high depth. And it's not so clear that you have any special advantage from this being quantum. Okay, I want to show one more sort of related or bit of an extension on this, and then we'll also talk about something called Boltzmann machines. But I think it's a good time for a break before that. Let's continue at the 1:15.